thank you, Andy, and it's nice to be here to talk in front of you. Putting together this talk was, I will say at the start, a challenge for two reasons. I received an email from Megan Fadley, who works with the Simons Foundation, and there were 2 points that she highlighted. One was that I'd be speaking to an audience of experts, but who are not in my field, and that's an unusual crowd because I'm used to speaking to experts in my field and speaking to non-experts not in my field, which is what I do when I teach the pre-meds and freshman chemistry. But of course, experts not in my field is an unusual audience to target, and so I hope I get the level right. But one way we can address that is related to the second reason why this talk was hard to prepare. Was Megan said that although there, I think, there's an hour allotted or 70 minutes or something like that, she said that usually you can only get to about 30 minutes of the talk because there's so many questions. I've written a talk which can be stopped at various places, and at the end of the day, I hope this is really just about having some fun, and I'll be able to tell a little bit about the things I think about, and certainly, feel free to ask things at any stage. Okay, so I'm a theoretical chemist, and as Andrew was saying, for many people, chemistry is really about test tubes and beakers and measuring cylinders and so on and so forth. But that's not really what I do, and indeed the last time I did an experiment was when I was actually doing some outreach in Puerto Rico, and I'm really, really incompetent when it comes to doing anything with my hands. And so we're making a battery out of fruit, and I couldn't get it to work, and so the kids had to help me out. And so if you ask, well, how am I a chemist really in any real sense of the word? And I think of myself as a chemist because I'm interested in the types of questions that chemists think about, but from a theoretical perspective. So I'll say a little bit about what some of these problems are. The first one is about catalysis. And this refers to the fact that in nature, we see lots and lots of remarkable reactions carried out by biological systems. Photosynthesis, for example, all plants do this. It's what provides the world with energy, with sugar, for example, and also replenishes the oxygen in the atmosphere. And they do this all day long under ambient conditions. And if we could do this, then we wouldn't need to be burning things like fossil fuels and so on and so forth. So it's quite remarkable that this chemistry can be done without, for example, creating a big engine, creating all this heat and all this exhaust and so on by plants. Another example of an interesting reaction is the one of nitrogen fixation. So this is the source of all the protein in animals in the world. So we get our protein, in principle, its ultimate origin is the nitrogen in the air. But the nitrogen in the air is very stable. We can't metabolize it directly. And we rely on little bacteria in the roots of leguminous plants who can convert this nitrogen into ammonia, which is the precursor of amino acids and the way we use nitrogen in our bodies. Now, this is a reaction that we also do as humans. In fact, there's a famous reaction known as the Haber process, invented about 100 years ago. And the ammonia that we extract from the atmosphere by converting nitrogen through the Haber process feeds about 1/3 of the world's population and consumes about 2% of the world's energy. So it's a very, very important process. But in comparison to the Haber process, which is done at 400 Kelvin and 200 atmospheres under extreme conditions, these little bacteria just do these reactions, very gently under biological conditions, standard temperatures and pressures. And so we observe that nature is able to do incredible chemistry under very mild conditions. And if we could do the same chemistry by mimicking nature, that would be fantastic. And so it's a problem that I'm interested in trying to address from the viewpoint of theory.
And you didn't tell us, but presumably we were going to guess that because this is called biocatalysis, part of the way it happens is through catalysts?
Yes. So I mean, these reactions might be sort of allowed in the sense of thermodynamically allowed, but they're just very slow. So, and so the main feature that biology is doing is somehow lowering the activation parameter. Another area which I'm interested in is the one of molecular materials. And we all use materials, of course, in some sense. And most of the materials that we deal with in our lives are not molecular materials, but more things like crystalline materials or amorphous materials. And an example of that is silicon. So silicon is a very widely used material. It's in all electronics. It's used in photovoltaics and so on and so forth. And a lot of effort has gone into optimizing silicon as a material, the production of silicon. So silicon is probably the first material that we come across in our lives. This entire thing that you see is the same size as a human. That's a single crystal of silicon. One crystal. You see, it's grown from a thread that they dip into a silicon melt and they pull out slowly. It's not so different from growing a salt crystal. And it's incredibly pure. So the defect density in here is about 1 part in 10 billion. So the fewer defects, it's harder to find a defect than it is to locate yourself in the world's population. So it's absolutely amazing what people do with all this energy that's been invested into optimizing the silicon as a material is absolutely amazing. But there are many limitations of silicon, put simply, crystalline silicon doesn't have great mechanical properties. For example, it's brittle, so you can't conform it to various surfaces, and it's also hard to modify the behavior of the material. So if you really wanted to change, say, the band gaps of silicon to make it better photovoltaic, there's not much you can do. So whatever you tend to do to silicon as a material tend to make it worse. So one of the holy grails is to make a molecular material, which is one where instead of using silicon atoms as the constituents, you can use molecules, and those molecules can be tailored, and you can have different molecules with different properties for different kinds of applications, and you can, for example, make them mechanically flexible and so on and so forth. As it is, though, it's been hard to make molecular materials which rival silicon, but nonetheless, that's what we'd like to understand how to do, make these materials which are tailorable at the molecular level, which we can use to replace crystalline semiconductors, for example. And then finally, another area which motivates my work, which I'm interested in, is the one of high temperature superconductivity, and this is something that's really on the interface between chemistry and physics, of course. And high temperature superconductivity is the phenomenon it's a phenomenon which has been known for about 30 years, and it refers to the fact that in certain materials, most notably the certain cuprates, they become superconducting when you lower the temperature below what looks like a high temperature for this phenomenon. So there are many superconductors in nature. A lot of elements become superconductors when you go down to, say, 4 Kelvin or something like that. But unusually, if you take these complex arrangements of copper and oxygen and other types of elements, this transition to a superconducting state can be observed at 100 or so Kelvin. So this is a phenomenon which is actually quite old now. It's been known for 30 years. It would be inaccurate to say that people don't understand anything about it. But at a detailed level, I think it's accurate to say we don't really know what's going on. So I'm interested in trying to understand from a theoretical perspective how superconductivity arises, say, from this detailed arrangement of atoms, from the microscopics. And of course, if we can do that, then we can try and create new tailored materials, perhaps with higher transition temperatures, or perhaps with better material properties than existing superconductors. You might ask, for example, why don't we see more high TC materials used in the world around us? And it's mainly because they don't have good material properties. They're ceramics, so they're not really very good for making wires because they're very brittle. Okay, So I want to do all this, but as I was saying, I don't want to do it by doing anything in the lab. And so I have to start with the physical theories. And the basic physical theory at the heart of chemistry is quantum mechanics. So this was recognized a long time ago by Dirac. I guess this is now 80-something years ago, who, after writing down his theory of the electron, the equation for the electron, noted that the fundamental laws for, you can notice the difference in adjectives here. For a large part of physics, and the whole of chemistry, which you will do, so I know where my place is, that's completely known. But as he also observed already at that time, the difficulty is that that applying these quantum mechanical laws, or trying to derive predictions from them, involves solving very complex equations. So we can ask, what's complicated about solving the quantum mechanical equations for a material? And that's really what's at the heart of the talk. What's the complexity of solving quantum mechanics? Is it when we say it's difficult, is it impossibly difficult? Is it sort of feasibly difficult? And so on and so forth. And that's something that I hope we'll try and understand over the course of the rest of this lecture. Okay, so I'll begin with a little bit of quantum mechanics, and sort of this. I noticed thereafter this is in the audience, so this will be very familiar to those. But to settle the problem, quantum mechanics involves a lot of the time solving an equation that we call Schrödinger's equation, which we can think of for time-independent quantum mechanics as a differential equation. This is a constant, and this is a differential operator, and this is the eigenvalue of the differential operator. And we're solving it for this function, which we call the wave function. Now, in the simplest case, if we have a single particle, such as a single electron in the hydrogen atom, and you'll notice that I'll talk mainly about electrons as quantum particles. So matter is made of electrons and nuclei. And nuclei are very heavy, so we don't think of them as exhibiting a lot of quantum effects. So we think of them as unimportant for the quantum mechanics. So I'll talk mainly about the electrons. So if you have a single particle such as an electron in the hydrogen atom, then this wave function, so to speak, is then just a function of the position of the electron. And we sometimes call this special wave function one electron in an orbital. So you can solve the Schrödinger equation for this function for this wave function. The wave function can be interpreted as related to the probability. So when I square the wave function, I get the probability distribution of the electron in space. And you get out various solutions. So as it turns out, there's part of the spectrum which is discrete, and the associated eigenfunctions have some shape that look like this. And they look a little bit like waves. So the solution, it really is a kind of wave equation. The electron looks a bit like a standing wave inside a spherical box. The validity of quantum mechanics can be checked by comparing the energies that you get out with the energies of transitions that you measure through spectroscopy. If you reduce this to its most bare bones level, the transitions are parameterized by, in addition to fundamental constants like the electron charge and so on and so forth, they're parameterized by a number called the fine structure constant. So you can compute this by theory, and you can derive it from spectroscopic measurement. And the two agree to, on the order of 1 part in a billion. So this is the most, one can view this as the most accurate theory there is in nature in terms of the agreement between theory and experiment. So we know quantum mechanics is correct. Now, so this is quantum mechanics for a single particle. Now, most materials have more than one electron in them. In fact, all materials have more than one electron in them. And so we have to think about many particle quantum mechanics. And this is where quantum mechanics starts to become a little bit more complicated, and where all the computational complexity arises. So it arises because of the possibility for entanglement in a quantum system. And so to say roughly what entanglement is, and I won't be very precise here, I'm going to introduce two scenarios. So I'm going to consider a classical world which has So an instance where there are two balls. And you know that if you have these two balls, I can sort of make an observation on one ball and write down its position, and I can make an observation on the other ball and write down the position. And for example, it doesn't depend on the order in which you do it. You should see the same result, or it doesn't. In some ways, it doesn't depend on what you measure here. You can measure this one independently, and you won't find correlations between those two measurements. Now, in the quantum world, it's possible to set up a scenario, to set up a system of two balls where I can carry out my measurements here of where this ball is and carry out my measurements there. And when I look at what I measure here and what I measure there, you'll notice correlations between the two. Now this is entanglement, not being particularly precise, but this is entanglement. Sometimes you can view it in a way which seems very mysterious. So sort of in the early days of quantum mechanics, this was viewed as like spooky action at a distance. Just that people would say, it looks like I'm measuring something and affecting the result really far away. And that's a particularly mysterious way to think about this phenomenon. You don't have to think about this way. All you have to all one has to accept is that in a quantum system, it's possible to set up a state where there are correlations over long distances from the very beginning. This is really all that is going on. But in any case, this phenomenon exists. It's a possibility in quantum mechanics. And the reason why this leads to complexity is that when you have a quantum mechanical system with many components, you can no longer talk about individual measurements or perhaps individual probabilities of measurement, but you must always talk about the joint probabilities of measurements. So this means when I go back to my wave function, which is some kind of probability, if I have a system with many parts to it, this probability amplitude has to depend on all the parts. It has to be a joint probability distribution. In particular, if these are particles like electrons, then this wave function is some simultaneous probability amplitude depending on all the electron position. And so it's clear that this is a function of many variables. And so if I were just to write it down or represent it, if I had one electron, you could put it on a grid or something. Or if you had two electrons, you could put it on a square grid, but the number of points is squared. And if you have three electrons, you have to go to the cube of the number of points. And so it's quite clear that when you have many, many particles, just the representation of the wave function becomes immensely difficult, exponentially hard. Okay, so quantum mechanics deals with, when you have many particles, deals with wave functions that are high-dimensional objects, and consequently quantum simulations of real materials, which have lots and lots of particles in them, on the order of 10 to the 23 particles, appears completely impossible, because it seems exponentially hard as the number of electrons increasing. Just writing down the wave function, let alone actually solving the differential equation to get it, seems impossible. So even if someone could give you the answer, you couldn't store it. So nonetheless, how did things proceed historically? Well, I mean, this exponential complexity was recognized very, very early on. I mean, it will be essentially when quantum mechanics was first discovered. But in the meantime, computers came along, and so people could crunch numbers much quicker than by hand. And so for many years, and computers kept getting faster. So for many years, people just did the best they could. And Popel, who was one of the fathers of my own field of quantum chemistry, basically said, you do the best you can, and all your calculations sort of lie somewhere in this diagram, and you can think about them as having the diagram of having a y-axis, which characterizes sort of the spatial resolution of your simulation, or the grid size. And then you can do calculations which are approximate, which do the quantum mechanics, say, of one particle correctly at a time, or maybe do two particles at a time, or three particles at a time, and so on and so forth. And these are all approximations. And if you did all the electrons, did rigorously the quantum mechanics of all the electrons at the same time, you'd be really solving this exponentially hard Schrödinger equation. Now, it's important to note that truncating this anywhere is something that, from this philosophy, was done just as a matter of feasibility. So there's no reason to expect that you could say just treat 2 electrons at a time, or at least Pope did not say that, did not argue that that was something you should expect. It's more like when you play a chess game, your computer has to search moves ahead, and in principle, it should search as far ahead. It should search an infinite number of moves ahead. But just in terms of feasibility, you may only search 4 moves ahead. There's no reason to suggest that that's the right number of moves to search ahead, but that's all it can do. And so that's essentially how people did quantum simulations before. You just do the best you can. So that's okay, but ultimately, it's kind of depressing, right? So unless you have some way to think about the complexity in a new way, this is just kind of saying, well, this is an impossible problem. You do the best you can, but most of the time you just cannot simulate things quantum mechanically. There are many statements in support of this depressing view, and one of them actually. So I got an email from Ernie or Ernest, yeah. A question before the lecture, and so he gave me this quote, which is, I thought, a good one. Blochman wrote, well, the Schrödinger equation cannot be solved accurately when the number of particles exceeds about 10. One way you get this number saying is by thinking about having on the order of 10 grid points per particle. So 10 to the 10 is already a very large number. Right? And no computer existing or that will ever exist can break this barrier because the catastrophe of dimension. And indeed, this point of view has been taken further by some people. Walter Cohen, for example, has long argued, and this was in fact in his Nobel lecture, that since you can never solve the Schrödinger equation for many electrons, it doesn't even make sense to talk about the wave function. It's not a legitimate concept, scientific concept. It's kind of a rather harsh view for large numbers of particles. Okay, so in this depressed state, many scientists sort of decided to turn away from trying to solve many particle quantum mechanics in a rigorous sense, and for that reason, in the last, starting maybe 30 years ago, what most people did when they actually needed to do a simulation of a real material was they did something called density functional theory. Okay, so what is density functional theory? Well, density functional theory is sort of basically giving up on the problem. And so basically Walter Cohen argued that since we can never really deal with many electrons explicitly, then what you do is you just do what you can. So you solve for, and the simplest thing that you can do is you solve for each particle's behavior independently, which is the wrong thing to do. Particles interact with each other. But then, when you've got this solution, which is not going to be the right one, you can add a correction to it. And this correction in practice is derived by, say, fitting to experiment. Now, there's a little more to this story, of course, and there's a formal foundation for density functional theory, which was involved with, which tells you that this correction here, in principle, is a functional of quite a simple object, which is the single particle density. And this is nice because you feel that it's a function of an object that's very simple, so maybe you can understand it. But of course, the complexity is hidden in the functional relationship between this simple object and, say, the observable that we want. But in any case, regardless of what one thinks about this in a philosophical sense, density functional theory was really revolutionary and changed the practice of quantum simulations, because it turned the quantum mechanical problem from one which was either impossible for large systems or sort of barely doable for a small number of particles into a calculation that anyone could do. So before DFT came along, the only people doing these quantum simulations were real specialists, real theoreticians. And then afterwards, particularly when computer programmed or written in a sort of user-friendly way, all the experimentalists start doing it. And probably today it's impossible to publish an experimental paper on a material without doing some kind of density functional calculation that shows some form of agreement. Okay, so this is a great success, even though in some ways it's a diversion from doing quantum mechanics rigorously. And for a while it seemed there would be nothing else. But of course, as one can imagine, many cracks began to appear in such a simple framework. Here I show you a very simple molecule, a very simple example. So this is the hydrogen molecular ion. So this is the simplest molecule you can make because it's only got 2 protons and 1 electron. And one doesn't really have to be a chemist to know that if you take 2 atoms, they could be bound at short distances, but if you pull them apart to infinite separation, the binding energy should go to 0. Right? Okay, so that's the exact result. In fact, you can basically solve this analytically. It's only got 1 particle in it with some appropriate coordinate system. And so there's the binding energy, and it should go to 0, and so that's the exact result. But here's density functional theory for most of the functions that people use, and you see this very, very peculiar behavior, even for the simplest molecule. And ultimately, it's because the correction that you're adding is some sort of average correction, and you know, most of the time you want to have a correction that takes into account interactions between electrons for the correction to be good for most materials. But here, there's only a single electron. There are no interactions at all. But you know, this correction doesn't know it's just some kind of fudge, and so it puts in some kind of weird interaction of the electron with itself and gets the problem wrong. Okay. So, although in a practical sense this was a very important step forward doing density functional theory, it just pushed the complexity of the many-body problem into some other piece. And in some ways actually made it more difficult to improve that piece. So radically, it's I think now well accepted that radically improving the performance of this very simple framework is very, very challenging, or perhaps impossible. And with this realization, which has come about really in the last decade, there have been many new efforts to go back to really doing the quantum mechanics properly for many electrons. And this has led to a real renaissance in quantum simulations, which is what I will talk about now. So at this point, I'm just going to pause. Maybe there's been not enough. Maybe there's not too much content. So maybe no questions. But I'm making sure everyone's doing okay. Yeah, everyone's okay. All right. Okay. So the main thing that people have recognized in the last decade or so is that although the quantum world formally appears very complicated, it has this exponential complexity. In almost all cases, well, not all, that's too strong a statement. In many, many cases, that complexity is really an illusion. And so the way one sees this is, for example, we know that there are many different kinds of quantum states which one could have in theory. So one can create Schrödinger's cat. Schrödinger's cat would be a superposition of a dead and alive cat, perfectly valid quantum state, but you don't see it, right? So there's some sense in which the world that we actually have around us, as opposed to an arbitrary, completely generic quantum world, is very special, and not all the quantum states are explored by nature. And so, if nature doesn't actually explore all the possible quantum states, perhaps all the possible entangled quantum states, then perhaps this exponential complexity, which arises by thinking that your wave function lives formally in the entire space of quantum possibilities, is not actually there. So what we really want to understand to move forwards is to characterize the physical subset of the quantum states that we actually have in the world. And so I guess this is sort of repeating the point. And so we're not considering, although the wave function is formally this complicated object, we're not concerned with just arbitrary states, but we're concerned in particular with the types of quantum states which are solutions to the Schrödinger equation for for Hamiltonians, which describe the interactions between particles, which actually have physical interactions. So one way to see why quantum states around us have a special structure is that the interactions between the particles, which are encoded in this operator, have special structure. If I take two electrons, if I take electrons, or electrons and nuclei, they don't interact with arbitrary forces. They interact with a very special force, the Coulomb force. And the Coulomb force is just a pairwise force. It's not arbitrarily complicated. It doesn't involve n particles at the same time, for example. So because the Hamiltonian has this simple structure, its eigenstates inherit that simple structure. Okay, what one might expect to emerge if I restrict myself to the physical quantum states is this sort of phenomenon of local realism. So although in principle, when one can set up quantum states where we have all these weird entanglements between distant parts, in other words, measurements are correlated between distant parts, in practice we know that such behavior is quite rare. So indeed, if I take two balls, I know that if I look at one, I'm not really, and I look at the other, those positions, those measurements can be done independently of each other. Or similarly, if I do something like try and perturb a system at one point, you don't see something peculiar happen, like the cat fall out of the end, okay, unless you're doing a magic show. So
when you say in practice they're quite rare, can you also say theoretically they're quite rare?
yes, so what we'd like to be able to show is that, for example, one can write down a Hamiltonian of a system quite easily. That's specified by sort of the fundamental forces. And so what you'd like to be able to show to make this a rigorous framework is that the corresponding eigenstates do not have these correlations in them. And that's something that has been proved in certain cases, not for all. So for example, it's proved in one dimension. It's sort of proved for some reason, some reasonable assumptions in two dimensions, so on and so forth. For Hamilton's work, yeah. Okay. So what we can expect to recover is that physical quantum states should actually preserve some measure of local realism, maybe not perfectly, but there should be some measure of locality. And they should only support a limited amount of long-range entanglement, because that's really what we see. Okay. So the way in which this really arises, in particular, let's say for ground states, to simplify things, is from the structure of the Hamiltonian. Okay. And there's a sort of more rigorous statement of what I'm saying, that physical states only support a limited amount of entanglement, and it's known as an area law. And what you just might have heard this term, and it just means that if I take a system and I divided it into two parts, and I call one part the inner part and the other part the outer part, then if I look at the quantum degrees of freedom, then only the degrees of freedom on this boundary can be entangled with the degrees of freedom outside. And so only the degrees of freedom associated with the surface area can be entangled. So that's the statement that people basically want to try and prove to be true, to show that the physical world is not so complicated, to prove the area. Okay.
So are you going to give a definition of entanglement?
Yeah. Yes.
Okay.
At some point.
Okay.
Yeah. Should I get there? So I can move past it. Okay. So that's the next thing. Okay. Yes.
With what you just showed, does it suggest that we just reduce the degree, the dimension by one, and the difference between area and volume?
Let's see. It's not as simple as that, because the Hilbert space, so the space the wave function's living in is equal to some number raised to, say, either raised to the power of this thing. So in a normal world, in an arbitrary quantum state, you'd have to think about some number raised to sort of the volume, and this is some number raised to the area. So the difference between area and volume is in an exponent, not in something.
That was the last one we can look at. And there you go. I think you're interested in this. Doesn't have a long spatial extent.
Yeah, it's, you know, it really doesn't, it's just a way of saying that locality. It's just a sort of precise way to say things are local.
It's like the only short range interactions, then, you know, if you carve out a part, the change is only proportional to the area.
Okay, so to make all this more precise, I have to write something down, which involves an equation. And so, you know, I did actually think, is when I looked through the list of, to the list of fellows, and there are various like biologists and so on and so forth. So I thought the crowd would be more, in that sense, you know, more diverse in that sense. That's why there's no math. But to make all this a bit more precise, I'm going to have to say what entanglement really is in a more precise fashion. And so let's take a system with two parts, the left part and the right part. So this might be one atom, and this might be another atom. And this atom might have a certain set of states labeled by N1, and this atom might have another set of states labeled by N2. And if I have a system which I set up to have no entanglement, so no correlations between the measurements, then the wave function, so that's a joint probability amplitude, of observing the first atom in state N1 and the second atom in state N2 should factorize into some product of probability amplitudes. And so entanglement just reflects the fact that this wave function doesn't factorize. And the way in which we quantify the entanglement is to write this wave function in a kind of factorized form, and we can interpret this in two ways. So this wave function is written as a sum of not probabilities, but you can think of these perhaps as partial probabilities. If you view this as a matrix, so it's something with two indices, then this is just writing as a product of matrices. You can think of this as a matrix factorization, like a singular value decomposition. From a physical perspective, you can think of this as these as joint probabilities, saying where I is some kind of message between the two systems. So this is like saying, I will see the atom in state N1 if it receives a message I from the atom in state 2. So this is like, that's how people would view it if they're talking about quantum coding. Okay, so a system which is not entangled just has one term in this sum, and a system which is entangled has many terms in the sum. And with appropriate normalization, the entanglement is just the number of terms in the sum, or logarithm. The entanglement entropy is a logarithm of the number of terms in the sum. So,
I'm sorry, is this, I should know this, but I'm embarrassed to say I don't. In what sense is this basis independent? Or
it's not basis independent.
It's basis dependent.
It's basis dependent, and so the point is that the world has a preferred basis, which is the spatial basis, and in that basis, the world looks very local.
Okay.
Yeah, or entanglement is low. So wave functions with low entanglement, or wave functions for two atoms or 2 degrees of freedom, which have low entanglement, the physical ones, would just be wave functions which could be written in this form, but with a small number of terms in the sum. So somehow physical states are restricted to things that can be written like this with a small number up here.
That's not like the top.
What's that?
That's not like the top. The top is completely independent.
This is completely independent.
Right.
Yes, but if I were to say, let me have two terms, that's not quite independent, but it's not as bad as having lots of them.
That's not independent.
Yeah.
So independent is no entanglement.
Independent
small
is
m
no
is low
entanglement.
entanglement.
And so generalizing this idea, so I could have three components, right? And three components, if they're independent, I could write this probability amplitude as a product of probability amplitudes. I use this word probability amplitude because the physical sort of probability measure, this is not a positive thing, right? So the physical probability is this thing, modulus squared. But something which is entangled would now be written as a sum of conditional probabilities. And in the same way, if I have a small number of terms in the sum, then I'm in a low entanglement regime, and the conjecture, which one can prove under certain conditions, is that the physical low energy states have no entanglement. Now, you can view this program of constructing these states as one where we replace scalars by tensors. So one way to say this is if I fix n1, n2, n3, so I ask the probability of measuring the system in a particular configuration, n1, n2, n3, in this case, it's just a product of numbers. Whereas here, it's a product of things which are not numbers. This is a vector times a matrix times a vector. So I'm replacing scalars by non-commuting quantities, which is in some ways what the general program of quantum mechanics is always about. So you usually replace, usually the way you go between classical and quantum is by replacing numbers by non-commuting quantities. And because they're not commuting, it depends on the order in which you write them or the way in which they're connected together. And so here I've chosen a particular way to connect these tensor probabilities, which you could represent by picture like this. So this is A n1 with an index I, and this is connected to A n2 with indices I and j, which is connected to A n3, and so on and so forth. But one could imagine other pictures that you can draw down that reflect the flow of information in the quantum state, or how correlations are transmitted between different components. And this, so in general, there's a network, and so consequently, we refer to these things as tensor networks. Tensor probabilities network together. This is an idea which emerged in the late 90s, although earlier, it's been used earlier, for example, in exactly solvable models by Rodney Baxter, if anyone knows that name. And here are people who, although many people use very similar things, here are names of some people who appreciated, I think, the bigger framework that this fits into. Okay, so the nice thing about this way of thinking about constructing this joint probability amplitude is it allows you to piece together a complex system just like by piecing together these probabilities of the individual components and gluing them together just like Lego. So you can imagine that if I have, say, a molecule or a crystal with lots of atoms here, then I could write down a probability tensor, it's not really a probability, something that looks like a probability, and then glue those tensors together in the same way that I glued them here. So here, this index I is gluing these two tensors together, this index j is gluing these two tensors together, and to reconstruct the entire quantum state. And you'll notice that because we never now refer directly to the joint probability of every degree of freedom at any one together, we immediately remove the exponential complexity associated with the quantum state. So it's very similar to saying, if I have a high-dimensional function and it's factorizable, then you just have to store the factors. You just have to think about the factors. Now, these factors are not commuting factors, so it's a little bit more complicated than that, but it's the same kind of idea. Now, of course, in doing computation, you have to do, so the storage is reduced to a polynomial problem. In actually doing computation, you actually have to contract all these graphs, and this is sort of, if they're computer scientists, then this is obviously well-known computer science problem, and if they have cycles, then that can formally be exponentially hard, but one can show that under most physical conditions, for most physical tensors, you can do the contractions, approximate them with polynomial times.
Wait, so where is the exponential complexity hiding? I mean, if you consider the entire space, is it that M in your previous thing is restricted, or are there states which simply can't be represented in this way?
Yeah. So the physical states, which is just a tiny quantum field space, have small m. To get to the entire space, you have to have larger.
So you would recover the exponential. So polynomial complexity is because the m is restricted to a finite value.
Yeah, to a finite value. Yeah.
Wait. First of all, each one of these balls,
yes,
in principle, is an arbitrarily complex quantum state. You're just kind of assuming something else, but in principle, nobody told you what N1
Oh, but I can choose a basis. So, and so n1 could be in any basis. So if I were to make a spin system, n1 is just up and so each ball is one spin. n1 is just
So
up
you're,
and down.
you're now considering
No, but-
very elementary,
Yeah, very, very elementary sort of components.
okay, well, and then saying that m is small,
Yes.
it's to some accuracy or for some class of states, which is what you're restricting yourself to. But you're saying it's a relevant class of states and it's acceptable accuracy. None of what you're saying is exact in any sense.
Well, so it's a question of if
This may take you too far afield.
No, that's an important point. So because in some ways this is the crux of the argument. So the argument which I haven't actually proved, okay, which I can go back to do. I skipped over that slide.
No, but you're saying it exists. The argument exists. There's
Yeah.
so-
Yeah, so for example, if I take, so to be precise, the case where it's absolutely concrete is that in one dimension, one can prove that if you take a Hamiltonian which has short range interactions and a gap, then it can be represented in an exponentially convergent way, so really with a precision that converges exponentially with this type of state.
The ground state.
The ground state.
No, but let's say not just.
Well, here, before we get out of hand, I'm sorry, if I may just, you had a
Yeah,
question.
I
Yes.
have
Is
a
that-
question.
Yes.
Your previous AN1 and AN2,
Yes.
why don't you use a conditional probability?
Maybe you can explain to me exactly what you mean. So if I go back to here.
Yes.
Yes.
So you have the top
Yeah.
AN1, AN2, AN3.
Yeah.
Instead of this, you can do AN1 given
N2.
N2 and AN2 given
Given
N3,
N3.
etc.
Yeah. So
Or
one could.
two of them, whatever. Why
Yeah.
don't you do it?
Oh, one could construct things like that. So that would be a. If you come from statistical mechanics, that's like the Kirkwood. That's like the Kirkwood approximation.
But these are approximate.
Yeah. So the thing with that is it's an approximation. That's like a very discrete approximation. So if that's not good enough, let's say there are only 3 particles in your system, and considering joint pair probabilities was not good enough. There's no way to construct a
But
better
you do
thing. Right?
conditional probability given.
Yeah. So I believe you're.
Distinct,
I believe you're saying if I have a probability of 3 things. Can you see it?
Yes.
Yeah. You can write it perhaps in terms of something which might look like this.
So that's a product of 3 pairs of conditional probabilities.
Okay, that's fine.
Right.
Yes.
that's an approximation.
Yeah. So this
Yes,
is.
that's fine.
Say. So one could do this, and
So why don't you?
so you mean why don't I personally, or what? So then I get, or I mean, why in principle one doesn't do it? So
Right,
so in principle this is an approximation, right? Isn't it? It's an approximation.
It's not an approximation, it's conditional probability. If
So-
you have a 2-dimension, you do
So there are
probability
types
of
of
A given B times the probability of B.
there are some functions of 3 variables which I cannot write in terms of functions of 2 variables multiplied together in this way.
Why not?
The
You can-
spaces are not the same size, right? So
You can always write conditional probability, right?
well, maybe you mean n1 given n2 and n3. Do you mean
Right,
that?
yes, I cannot really see what you want.
Okay, yes.
Given N2 and N3.
Yes,
That's
okay.
N times the
another way.
probability of N2 and N3, which you can divide.
Yeah, or you could write that.
N2 given N3 and then times P N3.
Yes, so you could write this would be fine. But the problem is the complexity of representing this conditional probability is identical to representing the full one.
And what you have here, there's no complexity in representing it.
No, it's not so much there isn't any, but what the hypothesis is that these numbers, the dimension associated with this index, or this index, or this index, is small. That's what characterizes the physical quantum state. So let's say it's 2 for all physical systems.
And what do you write under A of n3 given nj, and what else?
So
That's
for
it.
three particles, I would just stop
Okay.
here. Yeah. So, yeah, that is the.
So there was another,
Well, let's say you have an n by n lattice,
Yes.
which is our whole universe. We are not having a substructure
Yes.
inside.
Yes.
And we diagonalize the Hamiltonian.
Yes.
So what is the statement on the eigenfunctions? Are you
So-
claiming that below a certain energy, none of them would be entangled, or what would be the exact statement on the eigenfunctions of that Hamiltonian?
Yeah, so the statement is that if I were to take a particular, so let me make the easy statement. So let me restrict the Hamiltonian to have a gap. It's gaps, okay? And also let me make the Hamiltonian have short range interactions.
Which is not our world.
Well, the
it's
Coulomb,
part of it.
the Coulomb is it's a marginal long range, right? So in a charge neutral system. So if you make this statement, then I can say that the entanglement that I measure, or precisely in terms of the number of things I have to put in the sum, this becomes independent of the size of the system. Okay, so that would be the precise statement. Whereas in an arbitrary world, this number of terms would have to grow with the size of the lattice. The number of terms is reflecting the range of correlations. So if I have in a simplistic sense, if you have a system which has only where the correlations are not arbitrary and not arbitrarily long range, then the range does not grow with the system size. Right? Now, of course, now this becomes an issue when you go to a gapless system, and you can have some special long range correlations, and then you have some so then the M here has a logarithmic dependence on the system size, which is not that bad. Okay? It's not independent, but it's only logarithmic dependent. Yeah. It's a really interesting audience because, in most audiences, when you start talking like that I deal with, when you start talking about equations, that's when everyone has no questions. But this is the complete opposite. It's kind of a fun situation, right? So, okay, yeah, go on.
Let me ask a naive question. Suppose you have a molecule, you have electrons here and here, so
Yeah.
that is how far apart in the molecule do they be that you can consider the Coulomb force to be negligible?
Oh, no, that's quite far, but they have to be quite far apart. But on the order, so the question is related to the screening length in the material. So the Coulomb force is very, very long range, but what saves you is that systems are electrically neutral. In fact, if they're not electrically neutral, they would fly apart. Okay, so systems have to be electrically neutral.
They are not gravitationally neutral.
What's that?
If you're talking about the universe, they are not gravitationally
They're not gravitationally
neutral.
Yeah.
So
Yeah.
that's
Yeah. But so for systems, because they have this electronic, that means that you never feel the bare Coulomb force. You always feel, so for this thing interacting with a negative, so if this is one charge, let's say if it interacts with a negative charge, you always know it's going to be interacting also with essentially a positive charge of the same sign. So there's this screening, and the screening is on the order of sizes of atoms. I mean, it's not order of, it's not thousands of atoms, but you can expect it to die. Actually, I don't really. I mean, it's on the order of atomic units. I actually don't know. Actually, can't give a precise number. But if something is, let's say, 10 angstroms away, you would be quite small. So, should I continue? Yeah. Okay. So, okay. So the idea is that wave functions are sort of factorizable. That's one way in which one can understand this. And so, as a simple example, I will show you an actual calculation. So, on an actual set of atoms. So this is a set of atoms which They're just hydrogen atoms. So this is not a real molecule, because you cannot make a molecule like this in reality. But you can just set up a system where you put all the hydrogen atoms in a line. If I assume each hydrogen has a small number of states, I think here I'm assuming there are 4 states in each hydrogen atom, you can count the total size of the quantum space, which would be, say, 4 to the number of atoms, which would be a large number. Okay, so that's what this large number is, roughly speaking. And so clearly trying to represent a wave function in this space is too large. But I could write instead, well, this wave function, which depends on the state of each hydrogen, I could write it as a product of these partial probabilities or conditional probabilities in the way that I described before. And I can do it. I can solve the Schrödinger equation, which is an eigenvalue problem, and try and determine what these things are. And what you see is the following. So the conjecture is that I can keep the entanglement, which is the number of terms in the sum, so to speak, very
Which
small.
is K.
Sorry?
K?
No, the dimension associated with these indices alpha measures the entanglement. So K is the number of atoms. K is 50.
Oh, SK, I'm sorry.
Yeah, K
Right.
is 50. Yeah.
Right.
And then you see, I've introduced these additional variables. Actually, this should be alpha 1, so this is a mistake. These additional variables, which are summed over, which sort of glue the degrees of freedom together. They introduce correlations. And the argument is that in a physical system, the dimension associated with these indices should be very small. And here I've done 2 calculations, one where the dimension associated with these indices is, say, 250, and here one where it's 500. And I calculated the energy, the eigenvalue associated with these 2 approximate states. And you see that they basically agree to many decimal places, showing that in the physical system you don't really need a very large, there isn't much entanglement, so the dimension associated is small. In principle, to represent an arbitrary quantum state in the space of this size, this dimension would have to be on the order of 10 to the 28. In fact, it would be the order of the square root, it would be 10 to the 14. Okay, but we only need it to be 500 instead of 10 to the 14. Okay.
And what is RE?
Oh, yeah, so this is for different ones. So this is the distance between the hydrogen atoms, and they're in some units. And so this is 1 and 1, so I'm stretching the chain. So RE stands for equilibrium.
You're saying it, if anything, gets better with large R.
Yeah,
That's what
yeah,
you're saying, right?
yeah,
So there's question here.
yes.
So is there a way of saying it in words that something is only entangled with its neighbor or something like that?
No,
That's
250.
there is some entanglement. I'm sorry, I didn't really understand the question.
This chain.
Yes.
It's 50.
Yeah, things are basically entangled only with the neighbor and a little bit with the next neighbor, and very
So
rapidly it
that
dies
was
off.
my question.
Yeah, so that was that's what we expect.
I don't understand. Can you go, where is the short range
In
here?
the Hamiltonian.
No. But
Why did I say why is 250 a small number? Is that what you're saying?
yeah, or
The-
what is it measuring?
So so the logarithm of this number is precisely the entanglement entropy.
Yes.
Now, so that's a measure of how much information is encoded in correlations between one half and the other half.
Right, I know, I understand
Yeah.
that, but
Yeah.
you're always referring back to something which is purely geometric spatial in n dimensions. Here n is 1, and you're saying there's something short range. That's what I don't see. What is telling you that something is short range in
Oh.
space?
Oh, in space. Okay, I haven't
well, that's
computed
all.
any correlation functions to show that. But what one can prove is that if I have wave functions of this form, if I compute any correlation functions between 2 points, they decay as an exponential with an exponent depending on the size of this m. So if m is small, they decay very rapidly.
If the log of m is small,
Or the log of
then they decay on a spatial range which is of order log m. Is that sort of what you're saying?
Well, there's some conversion of units from log m to
Okay,
distances, yeah. But yeah,
which
yeah,
depends on,
yes.
and that's why you're referring to space,
Yeah.
which is not
Yes.
obvious at all here.
Okay, yeah, I think, yes.
But to restate, and then we should probably think about winding up in a few minutes, but to restate, if this is a class of, let's say, variational wave functions,
Yes,
which would become exact as m goes to infinity,
yes,
and for any finite m, these variational wave functions can only describe states with a finite correlation
yes,
length, whose length depends in some
On
way
m.
that we can discuss.
yes.
And the remarkable fact is that this class of variational wave functions turns out to be the ones that you need to represent the ground state.
With finite correlation.
Yes.
Yeah.
Is there some assumption about the Hamiltonian here?
I am using the physical Hamiltonian, but the assumption of locality is related to the fact that the Hamiltonian has two special features. One is that the interactions decay with distance, and the second is that the interactions are not n-body in nature. I mean, they're two-body, you have two Coulomb interactions only two body.
So it's nearest neighbor interactions.
No, they need not be nearest
No,
neighbor.
pairwise.
But they're
Pairwise.
Ah,
pairwise and not too long range.
Pairwise are not too long. I mean, it gets worse if you have 3 and 4. Things will still be true, but things would be harder.
and
But
that's what allows you to write this with a bound on the number and
with a bound on
space of
alpha.
alphas.
Yes, and I mean, this bound was not obtained through mathematics. It just did a calculation with two different values, and you saw that the
Of n.
of m, yeah, you don't see anything changing. Okay, so this language, so in some ways you can think of tensor networks like a new language of quantum mechanics, and it has many implications for fundamental physics. So I don't know how much time there is.
Well, not so.
Not so much. So it has an impact in many areas. Okay. So I was going to say it's a natural successor to the idea of the renormalization group, and maybe I'll say a little bit about that, and then I'll stop. So when one says new language, there's no new quantum mechanics in it, but it's in the same way that when Feynman introduced a path integral, there's no new quantum mechanics associated with the path integral. It's just a reformulation, but some things become very clear when you write them in terms of the path integral. So similarly, some things become very clear when you write them in terms of tensor networks. Okay, so renormalization group, I won't go into in great detail, but in the 70s, it provided the link between microscopic theories and some macroscopic behavior, particularly in critical phenomena, and I don't have time to talk about it. One way in which you can think of the tensor network as a generalization of the renormalization group is the following. So this is a quantum system with degrees of freedom for the atoms, and you can interpret these connections here as the renormalized degrees of freedom. So the way you look at this picture, so this is just a picture for the structure of the state, but really what you can rigorously interpret it as is this is a state, and these are the renormalized degrees of freedom associated with this atom. Here I have two atoms, and this I2 index, it refers to the renormalized degrees of freedom for the two atoms, and so on and so forth. So this is the renormalization group flow direction in the state. And you can see, so renormalization group is just a theory of linear tensor networks from this perspective. But because you've introduced this more general language, you can construct much more general flows of information. So in RG, you just flow from one scale upwards to its core scale, but here you can flow all over the place. So then I talk about classifying phases, and I'm going to stop. So there's a lot of stuff. This is actually the applications to some real things, and I'm not going to talk about that, but there's some superconductivity stuff. Okay, so all right. So this is the end. So in a nutshell, quantum mechanics is not so bad, and tensor networks give us a language in which to think about quantum mechanics in sort of physical subspace. Okay.
Thank you.